A very good morning, good afternoon, good evening to all my dear friends, participants and students for this NPTEL MOOC course, the title of which is Application of Forecasting, Regression and Time Series Models. My good name is Raghunandan Sengupta from the IME department at IIT Kanpur. Now, the three broad areas being covered in this course are respectively forecasting, which you have already finished, regression, and the last one in time series, and we are doing the ideas and concept of regression. This is week number 9, we are starting the week number 9 and this is the lecture number 41. What is the coverage? The coverage which you see is exactly equal in words as we did in the 40th lecture, because we are continuing discussing on that aspect. So, it will be LINEX loss functions, expected value of loss and risk of estimation. And another topic which I have not included would be the balanced loss function, which I said. So, depending on the coverage as we proceed, the slides would be changed accordingly. So, and when you listen to these lectures, video lectures and consult the slides, that would make sense, because if you remember, after each class I update the slides depending on the whether there are some minor errors or whether some coverage has been done extra or we are not able to do that, that is updated accordingly. Similarly, the Excel file you see in many of the classes where I solve the problems is exactly updated and it will be shared to you accordingly. Now, if you remember, we were discussing in qualitative sense that the environment being LINEX, which I will mark with a certain color, the environment being LINEX, I should use the highlighter, the environment being LINEX here also, and in one case the estimate you are using is LINEX, that means same environment, same estimate, and in the other case the estimate being utilized is not LINEX, it is squared error. That means environment same, again repeating, environment same, estimates being different, and it can be proved theoretically. Theory is not needed for this course until and unless it is really required to understand the concept. So, there are some steps in the proofs. So, once you have it, you are certain that the, I will use the color green, the risk under LINEX environment, and if you are utilizing the squared error, S is the squared error, this loss would be greater than equal to, here it is less than equal to, just I am taking them on the other side, is greater than equal to the risk, I will use the blue color, risk under LINEX, and when the estimate is also LINEX. That means, same environment, same estimate would give you lower quantum of risk, which is good, and we will show it with detailed simulation. I will only give the results. Again the same problem we are considering, trying to find out the returns for Tata Motors given the returns for NSE 50, rupee to India, US dollars in rupees and the Brent crude price in euros, and also we are considering beta naught, the intercept is there. Considering that, we have 4 beta values, beta naught, beta 1, beta 2, beta 3 and their corresponding estimate value, considering that sample of 99 in number, if you remember, the beta value had values come out to be this. We have already seen it. Theta hat value comes out to be plus 1.04 560, we have already seen it. Sigma square is 0.0052, that is for the estimate, but actually should be less if you keep repeating and take different samples. Based on that, I do the calculation. What I do is what will be shown in the next slide. It is like this. In column 1, first one you have the A values, again minus 1, minus 0.75, 0 plus 0.75 plus 1. Corresponding to second and third column other risk, yes, under the LINEX environment for both of them, yes. Second column is the estimate is squared error here, and in the third column the estimate is LINEX here. And if I put it in the formula which you have already seen, which seems complicated, but it is not, the values of risk for LINEX loss squared error estimate comes out to be these values, second column. The corresponding values for LINEX loss environment and LINEX estimate comes out to do with this third column. We find out the difference as we have been doing it in the earlier cases also. Very interestingly, for A is equal to 0, both the risks are 0, because A values being there and you are considering the estimate not being there, that you are trying to find out, the difference is 0. And if you consider the values of the differences, now both are plus for minus 1.0 A and plus 1.0 A, because the reason being A is being taken as squared. So, negative values will not matter there, but very interestingly they are of equal quantum. So, minus 1.0 value of A plus 1.0 value of A, the difference comes out to be 0.3925 as shown here, which I am circling, and correspondingly you can find out the values here. I have only given you in the snapshot table few values. Now, what I do is that I plot them, and I plot them with the concept that along the x axis I have the values of A, starting from minus 1.25 to plus 1.25 as shown, and as I am marking with the black A values, positive, negative. Along the y axis I plot the risk of LINEX with LINEX environment squared error estimate, other one being risk being LINEX environment LINEX estimate, and they are correspondingly given by the coloring scheme of red and blue. Red being for risk, environment is same, so I am not going to repeat that. So, risk being when you use the squared error estimate, the red one, the blue one being risk being when you use the LINEX estimate. And very interestingly, the values which you have seen, the difference being positive, which means squared error is more, the estimate of risk is more, the values always given by the concept of LINEX loss estimate being utilized under LINEX loss environment, the risk is always low, which I have been telling qualitatively. Now, it is being shown theoretically by the proof. I only stated the result, not the detailed proof, and here is the simulation. And the question can be that, can we do that? We are doing it for the case of theta hat. So, as I replace the idea of theta with 1 0 0 0 and only consider beta naught, you can draw the graph. Beta naught under the estimate of ordinary square and beta naught under the case of LINEX loss estimate, and compare them when the environment is LINEX. Similarly, you can do it for beta 1 only considering L as 0 1 0 0 0. So, it will be beta naught, beta 1, beta 2, beta 3. So, in that case it will be Again I am repeating 0, 1, 0, 0. Similarly, you can do it for beta 2, where you will consider L as 0, 0, 1, 0, that vector, and finally you will utilize the value of L as 0, 0, 0, 1, where you find out beta 3. So, given this picture, you can find out the risk, compare the risk, find out the estimate under different environments using different concept of estimate, either the squared error or the LINEX. So, at one go you have all the informations for comparison. Now, for all these three lectures, I have been only talking about theta, theta, theta or beta, never mentioned anything about y and y hat. And you may be thinking, well, the idea is to do a good multiple linear regression, where the actual output is y, but y values or their estimate is never being discussed. Only the concentration was on beta and corresponding theta with their respective hat values. Now, here in this slide we are coming to the main focus, where if you compare the first bullet point is actually the formula of y hat under the squared error loss. Now, if you see this one, x star is a particular value of x. So, you have done this regression model to find out the beta hat values for n data points. Now, once the nth plus 1 values of x's are there, which is shown by x star, utilizing that x star values, you want to multiply with already found out beta hat values and proceed to find out y hat for the next value, which is nth plus 1 value. So, again I am repeating, you have utilized n observations, found out beta hat, but that is not the end of the task. The task is to basically find out finally the y hat values for the next time period, and that is what we are doing. Once you have this x star values, which is for the nth plus 1 time, you utilize that, multiply it by beta hat and find out y hat for the nth plus 1 under the squared error loss. So, having said that, we have considered all the ideas. I will continue, but just a flashback. We have considered all the ideas to find out beta hat, find out the error terms, find out the R square, adjusted R square, best estimate, all these things. Once we find out y hat, our task is not yet done, because the question would immediately arise in your mind that we have been discussing theta hat under a different environment LINEX. Is it possible to find out y hat under that different environment LINEX? Answer is yes, and this is given. The formula for y hat LINEX, again only the end result, not the proofs, is given, which I have marked in the violet one, is this. So, this term is exactly equal to y hat under squared error, and the subsequent term which you see, a value we know from the LINEX, sigma square we know from the error, x transpose x inverse we already know, we have been doing it and utilizing so many times, and this value of x star transpose and x star are exactly the nth plus 1 term. And if you want to find out what is the dimension, I will go to that. So, if you remember, I will use the coloring scheme again back. So, the dimension for beta was k cross 1. Hence, the dimension of x star transpose would be actually given by, wait, yes. So, there would be values of 1 cross k, because there are k number of x values, x1 to xk. So, when you multiplied 1 cross k into k cross 1, the value of y hat LINEX is 1 cross 1 as it should be. Now, if I use the same concept, obviously this term is also 1 cross 1, and what is the second term on the right hand side? This looks complicated, it is not complicated, because if you pay attention here, we already know X star transpose has a size of 1 cross k. This we already know is k cross k, and this term will be k cross 1. So, when I have, and this a sigma square by 2 is just a constant. So, if I have this term inside the curly bracket 1 plus, and what is the dimension of the term? 1 cross k into k cross k is 1 cross k, 1 cross k into k cross 1 is 1 cross 1. So, the value at the end of the day when you find out y LINEX is also a single value, a scalar. So, the concept of dimensionality has been taken into consideration. So, there is no confusion. So, what is X star we know, and based on that we proceed. So, now we need to compare y hat square error loss estimate and y hat LINEX loss estimate. And here I have taken some values of y, actually the same data set, where we are finding out the return for the Tata Motors utilizing return for the NSE 50, Indian rupees to US dollars in rupees, and Brent crude price in euros. Now, the first column is I have taken some values for y, arbitrarily I have taken some values. Corresponding to that, the a values is already kept fixed as minus 1 in the last formula. So, the third column gives you y hat under squared error, fourth column gives the y LINEX under the LINEX loss. Now, immediately a question may crop up that there is a huge difference between y and y squared error or y and y LINEX, which I agree. But the main focus is to compare third column and fourth column, that is why I have marked. So, if you consider the third column and the fourth column, very interestingly for negative values of a, the value, because there was a minus a, so obviously that term in the last equation there was a minus a. So, minus of minus 1 will become plus, hence the second term is slowly increasing the LINEX loss estimate y LINEX with respect to y squared error, and that which you see in the difference. So, y squared error is, to read one value, is 0.0836 and the LINEX loss estimate is 0.0866. So, the value of y LINEX is more. Similarly, if I take the last value in the last row, the y squared error is given by, for minus a value is given as minus a value means I am taking different values accordingly and then calculating, because that will be X star transpose into beta. It comes out to be plus 0.1158 and the LINEX loss comes out to be plus 0.1186. Again LINEX loss estimate of y is more, as it should be. Now, I repeat this study. Repeat this study in the sense I do it for a value as minus 0.75. So, a values are given in the first column fixed, second column are the corresponding same values of y, actual values. Third column and fourth column which are to be compared are the corresponding y squared error and y LINEX. Again you see y LINEX values are more because it is minus a. And to give a comparison, if you consider the third row, the y squared error is plus 0.1046 and y LINEX is plus 0.1067 more. If I consider the second column, the value of y squared error is plus 0.1246 and the value of y LINEX is plus 0.1266. Now, interestingly, this I take the value of A as 0, again the same set of y, and I do the calculations, find out y squared error or y LINEX. Now, remember that term on the right hand side to find out y LINEX had A multiplied by those concept like A into sigma square by 2 and in the curly bracket 1 plus x star transpose and all these terms. As A is 0, that whole term will vanish, and as it vanishes, very interestingly, if you see the third column, fourth column values, when you compare y squared value with y LINEX, all of them are equal because A is 0, as it should be. Now, let us consider as A becomes positive, because positive will bring down the value of y LINEX. Let us see. As I do it for A positive, first column, all being 0.75, the second column is y value, and what is important is to compare third and fourth column, which are the corresponding values of y squared error and y LINEX for those corresponding values of y, and A being 0.75 for LINEX. And very interestingly, if you see, when you compare the third row, the value of y squared error is 0.1374 and y LINEX is 0.1354, and it is here seen immediately that y LINEX is lower as it should be. If I consider the last row, the value of y squared error is 0.1158 and the value of y LINEX is 0.1137, again y LINEX is lower as it should be. And finally, if I consider A value as plus 1 and compare the values of third row column with fourth column and do this comparison, again if I see the third row, the corresponding values of y squared is 0.1374 and corresponding value of y LINEX is 0.1348, and LINEX estimate y is low. And this is very much evident in this slide, as well it was evident for other values of A positive, and the reverse, that means LINEX estimate being more, is evident in the previous slides when A value was minus 1.0 and minus 0.75. Now, with this we have covered a huge bulk of area of the concept of squared error estimate of y, squared error estimate of beta, then for theta, did it for LINEX loss, compared the estimate of y, compared the estimate of theta or beta, compared the estimate of risk, and we are quite comfortable in the sense that we have the formulas and you can utilize that depending on the environment where what you want to work. Now, if you remember, I had mentioned that the idea of combining both is also very interesting, and that gives a very unique way of trying to handle the multiple linear regression, where you consider the loss function as a balanced loss function. What is balance word here? Balance word here, you are trying to balance the concept of two different losses under two different concepts, not environment, concepts. Here the concepts are the concepts of goodness of fit and concept of precision of estimation. Now, if you remember, once you find out beta, you utilize that and try to find out y hat. So, all the concentration was to basically find out the estimate of beta, and based on that find out the estimate of y. So, all the effort was gone in first step. But what if we put our effort in some way trying to find out first the idea of how precise your estimates are, and then basically compare how precise your goodness of fit is. So, precision is first on trying to find out the beta, and then goodness of fit is trying to find out the idea of y. So, we will go step by step and do it in 2 steps and combine these concept of losses and formulate the problem as a balanced loss function, and it was proposed by one very famous statistician. Now, this balanced loss function, if you see technically, it consists of these following component which I will highlight. Here also again delta is the difference between the estimate and the parameter, which we have already considered in the nomenclature. Based on that, we have 2 component of the loss. The first one, which I will mark with the light blue color, is the goodness of fit, and second one, which I will mark in the green one, is the precision of estimation. And precision estimation is very unique here, and we have already discussed, because depending on how you are able to find out theta, you are able to find out beta, because finding out beta will give you theta, and finding out theta you can find out the functional form of the goodness of fit. Goodness of fit can also be put as the idea corresponding to finding out the difference between y and y hat. That is one important fact. Number 2 is, if you see this equation of balanced loss function, the part of goodness of fit and precision of estimation both are squared, because if you take the transpose as you had seen with and multiply by its own, it is a square, because the transpose being taken because it is a vector. And both, again I am repeating, goodness of fit and precision estimation both are squared. So, when you find out theta using the concept of squared error, it will give you the OLS estimate, and when you proceed to find out y and y hat differences, again you are using the OLS estimate, which means that now it will give you some idea that what if we take a different environment of loss. Do we get interesting results? Answer is yes, and this we will consider in the next class and highlight that how different ideas of loss can give you a huge gamut of information of the estimate for betas and thetas, as well as for the forecast or prediction of y values. With this, I will end this class. Have a nice day and thank you very much.